2.3, Biconditionals and Definitions. This lesson is an extension of the last lesson, and our objective is to write biconditionals and to recognize good definitions. A vocabulary word here. A biconditional is a single true statement that combines a true conditional and its true converse. So remember last time we wrote converses. The converse was the reverse of the conditional. We have our if-then statement, and then we reverse our hypothesis and conclusion, our requirement and result, to write the converse. And if and only if statements, biconditionals, use the if and only if phrase. That's what joins the two together. So let's look at an example here. What is the converse of the following true conditional? So we're told that our conditional is true. If the converse is also true, rewrite the statements as a biconditional. All right, so our conditional says if, this is our requirement, if the sum of the measures of two angles is 180 degrees, then the two angles are supplementary. So if they add up to 180, then they are supplementary. And we know that that is true. So now we write our converse. So we switch the two. If two angles are supplementary, then the sum of the measures is 180 degrees. Now, is this true? Well, what's the definition of supplementary? Supplementary, we know, means that the sum of the measures of two angles is 180 degrees. So we know that this is a true statement. So we have a true conditional and a true converse. That says we are allowed to form the biconditional by joining the true conditional and the true converse with the phrase if and only if. So we are going to say that two angles are supplementary if and only if the sum of their measures is 180 degrees. We could also switch it around because it's true both directions. The sum of the measures of two angles is 180 degrees if and only if the two angles are supplementary. Notice we don't have any if-then statements here. We simply have a statement and then if and only if the other statement. So we took our supplementary portion and our sum is 180 portion, and we join them together if and only if. This is a better direction. Having supplementary first is a better direction because the definition of supplementary is the sum is 180, and we will get to that shortly, why we do this way. So go ahead and pause the video and you try the next one. Okay, our conditional, here's our conditional, says if two angles have equal measures, then the angles are congruent. And that's a true statement. We know that equal measure means congruent. So then we write our converse. We switch our two parts. We switch the hypothesis and conclusion. So if two angles are congruent, then they have equal measures. And that is also true. Congruent means equal measures. We know that by the definition of congruence. So since both are true, we can write them as a biconditional. And the bi prefix means two statements. And so we have two statements that are true, and it's true both directions. So which one are we going to put first? Well, we are defining congruence here. So two angles are congruent if and only if they have equal measures. Now, this one would be okay is if we said if two angles have equal measures, then they are congruent. Or if two angles have equal measures, if and only if they are congruent. It's true both directions, right? Our conditional and our converse are both true, but it's better to write it because we are defining congruent. So let's look at our key concept here. A biconditional combines, this is our conditional, here's our conditional, here's our converse, and then look at our notation. This says if and only if, right? This says that it's true both directions. P implies Q and Q implies P. So our arrow here, our double arrow, says if and only if. Our example is a point is a midpoint if and only if it divides a segment into two congruent segments. So we're defining midpoint here. We know the definition of midpoint is divides a segment into two congruent segments. Now, if we're given a biconditional, then we can write it as two conditionals that are converses. So let's look at our example here. We can keep some of this. What are the two conditional statements that form this biconditional? A ray is an angle bisector if and only if it divides an angle into two congruent angles. So what are our two parts here? We have a ray is an angle bisector and divides an angle into two congruent angles. So the first thing that we're going to do is we're going to write one of them. It says a ray, I want the other color. Ray is an angle bisector. So if a ray is an angle bisector, now we are putting our if back on because we are writing conditionals. This is our conditional. Then it divides an angle into two congruent angles. And then we're going to write the converse that says if a ray divides an angle into two congruent angles, then it is an angle bisector. See how we took our two parts and just turned them into if-then statements. Now it's your turn. Pause the video and do the next problem. All right, this shouldn't have been too bad. We have a biconditional here. Two numbers are reciprocals if and only if their product is 1. So I'm going to take one of the parts and put an if with it. If two numbers are reciprocals, and then the other one, then their product is 1. And then for the converse, I'm just going to switch that. If the product of two numbers is 1, sometimes you have to add a few words and change the order, so it makes a nice sentence. So if the product of two numbers is 1, then they are reciprocals. So that's not too bad at all. Now we are going to talk about definitions. A good definition has some important components. Number 1 here, it uses clearly understood terms. And these are things that are commonly understood or already defined. No words that need extra definitions. We talked about things like point, line, and plane that we are going to use to define everything else. The second part is that it is precise. You do not use words such as large, sort of, almost, kind of, close to. Okay? You must be precise. And finally, a good definition is reversible. That means that we can write it as a true biconditional. This is our if and only if statement. That means that your conditional is true and your converse is true. So you have to have a true conditional and then be able to write it as a true converse. And then you have a good definition. So if you look back at the biconditional statements that we were working with, okay, two angles are congruent and have equal measures, or two segments are congruent, equal lengths. Okay, so that is why congruent went first, because the definition of congruent is equal measure, equal length. And what was the other one? Angle bisector divides an angle into two congruent parts. Midpoint divides a segment into two congruent segments. Okay, so you can see that the first part of your biconditional is the word that you are defining, and the second part is the definition. Now they can be written the other direction, but one is correct, the other one is just better. All right, let's look at some examples of these. Is this definition of a quadrilateral reversible? If yes, write it as a true biconditional. So we have a quadrilateral is a polygon with four sides. Well, the first thing we need to do is turn that into a conditional. So we have to find our separation point. What are the two things we're talking about? Well, quadrilateral and four sides. So we have the idea of a quadrilateral, and we have the definition is four sides. Now we're going to figure out how to fit the word polygon in there. Remember, sometimes we have to add some words and move things around to make nice sentences. So we're going to write our conditional. So we take if a figure is a quadrilateral, then it is a polygon with four sides. We write our converse by switching those. If a figure is a polygon with four sides, notice we added figure to both of those, then the figure is a quadrilateral. So let's check these. Is the first one true? If a figure is a quadrilateral, then it is a polygon with four sides. That is a true statement. If a figure is a polygon with four sides, then it is a quadrilateral. That is also true. If you have four sides, you're a quadrilateral. So now we can write this as a biconditional. So which one of these words are we defining? Quadrilateral is the word we are defining. So a figure, remember, no if, no then. A figure is a quadrilateral if and only if it is a polygon with four sides. And polygon is important here because polygon is closed figure. You have to be a closed figure with four sides to be a quadrilateral. All right, so pause the video and see if you can do the next problem. All right, let's look at this. We wrote our conditional. We took the two parts. We have straight angle and measures 180 degrees. So if an angle is a straight angle, then it measures 180 degrees. Then we write our converse. If an angle measures 180 degrees, then it is a straight angle. So if an angle is a straight angle, measures 180 degrees, that's true. If an angle measures 180 degrees, then it is a straight angle. That is also true. That allows us to write a biconditional. What are we trying to define here? We are trying to define a straight angle. So we're going to put that first. An angle is a straight angle if and only if it measures 180 degrees. Now, is this a good definition? Well, does it use common, generally understood terms? Yes, we know straight angle, we know measure 180 degrees. Okay, those are easily understood terms. Is it precise? Yes, 180 degrees is very precise. And straight angle that is a specific classification for an angle. And is it reversible? Yes, it is. Our conditional and its converse are true, so it can be written as a true biconditional. That means we have a good definition for a straight angle. All right, and the last part here. One way to show that a statement is not a good definition is to find a counterexample. And you know what a counterexample is? It is just one instance that makes your statement false. Right? One example that makes a statement false. So let's look at it. Are some problems here. Which of the following is a good definition? A fish is an animal that swims. Are these understood terms? Yes. Is it precise? Yeah, mostly. Swims might be a little bit, what do you mean by swim? And is it reversible? So if we say, if an animal is a fish, then it swims, that's true. What if we switch it around? What if we say, if an animal swims, so we put in if a fish is an animal, if an animal is a fish, then it swims. What do we put in? If an animal swims, then it is a fish. Does that work? No. Can we find any counterexamples? Most definitely. Dogs swim, cats swim, dolphins swim. Lots of things swim. Giraffes, I believe, could possibly swim. I don't know. I assume pretty much everything knows how to swim. Elephants swim. All right, let's look at the next one. Rectangles have 4 corners, so let's split this up. If a figure is a rectangle, then it has 4 corners. Is that true? Yes, that one's true. Let's switch it around. If you have 4 corners, then you're a rectangle? Definitely not. All of our quadrilaterals have 4 corners. So any quadrilateral that you can think of has 4 corners, not a rectangle. So definitely not a good definition. Oh, we didn't go through. Are they commonly used terms? Yes. Precise. 4 corners is a little bit questionable again, but not terrible. All right, let's look at the next one. Giraffes are animals with very long necks. So if an animal is a giraffe, then it has a very long neck. That's true. Giraffes have long necks. Let's switch it around. If an animal has a long neck, then it's a giraffe. Well, we didn't do our first parts. Commonly understood terms. Very long is bad. This is already a bad definition. What does very long mean? Understood terms, yes. Precise, no. Reversible, no. An ostrich has a long neck. Snapping turtle has a long neck. Pretty sure we can find lots of examples of animals with long necks. All right, let's do the last one. A penny is a coin worth 1 cent. Let's start where we're supposed to start this time. Commonly used terms. Yes, those are easily understood. Precise. Yes, penny, 1 cent. Good precision there. Reversible. If a penny is a coin, or if a coin is a penny, then it is worth 1 cent. Let's switch it around. If your coin is 1 cent, then it is a penny. I think we have a good definition here. It has common terms. it is precise, and it is reversible. It meets all three of our criteria. So we have a definition. A coin is a penny if and only if it is worth 1 cent. That would work. That would be a nice definition. All right. Pause the video and do the last few problems there. All right. There might have been a couple of ways to go about this. Oh, let's do A first. Is the following statement a good definition? A square is a figure with 4 right angles. So we break this down. We have square and 4 right angles. So if we say if a figure is a square, then it has 4 right angles, that's true. But if a figure has 4 right angles, then it is a square, not reversible. Rectangles have 4 right angles. Oh, we didn't do it again. First, does this use common terms? Yes, common terms. Is it precise? Yeah, 4 right angles. That's pretty precise. We could go with that. But it's not reversible. So it's not a good definition. Even if it uses common terms and it's precise, still not a good definition because we can't write it as a biconditional. And the last one here, we have a statement, obtuse angles have greater measures than acute angles. Yes, that's true, but it's not a good definition for many reasons. First, does it use common terms? Yes. We know all of, these are all pretty common terms. How about precise? Greater measures is not precise, and comparing it to acute angles is another word that we can define. We want like already defined information instead of defining it using something else. So we need to make it more precise. And we want something that's reversible. So let's figure this out. We can write obtuse angles have measures, let's be precise here, between 90 and 180 degrees. So let's try that out. That has common terms. It's precise. Measures between 90 and 180 degrees is very precise, much more so than comparing it to acute angles. And let's see if it's reversible. So we write our conditional. If an angle is obtuse, then the measure of the angle is between 90 and 180 degrees. That one's true. I like that. Obtuse, and yep, that's what obtuse is. And it's converse. If the measure of an angle is between 90 and 180 degrees, then it is obtuse. Yes, that's also true. So this is reversible. We now have a good definition here. Obtuse angles have measures between 90 and 180 degrees. And we could write this as a biconditional. An angle is obtuse if and only if, right, it has measures between 90 and 180 degrees. So now you can see what we were talking about at the beginning of why biconditionals are used, are basically just definitions. So these are pretty straightforward. Again, the most difficult part of this is going to be thinking about and finding those counter examples that would make it false. Make sure that when you are thinking about what makes a good definition, that you use all 3 of our criteria that I neglected to do on several of these. Sorry about that. 1, it has to use common terms, things that are easily understood. 2, it must be precise. Okay, make sure you're not saying sort of on these things, or almost. That is not precise. And 3, it can be written as a true biconditional. It is reversible. You use your conditional and its converse, and they both must be true. So make sure a good definition has all 3 of those pieces. All right, I think this is going to be another homework that you do very well on. So let's go have some fun with that.